Energy. So now we're going to take what we learned about work and potential energies and use energy conservation to solve a problem. We've got two masses and an inclined plane and a pulley. We make some assumptions about this system. The rope is massless, makes it a little simpler for us to solve. Massless pulley, frictionless pulley. We actually don't have the tools to deal with a pulley that has mass yet, but in a few weeks we will, and we'll have pulleys with mass. The neat thing about a pulley that has mass is that the tension in the rope on either side of the pulley is different. But when our pulley is massless, the tension is the same everywhere in the rope. I've gone ahead and drawn free body diagrams. You might be wondering why I drew free body diagrams. We're not using Newton's laws to find an acceleration. We could use Newton's laws, find an acceleration, and then use our kinematics equations to figure out how fast the mass is going before it hits the ground. But I think it's easier just to use energy. But the free body diagrams will help later on. We're going to need to figure out the work done by friction, so we're going to need to know what the friction force is. So I like to start out with free body diagrams. The key to using energy is not to double count the contribution from some of the forces. So in order to make sure we don't double count the contribution from some forces, we need to very carefully define our system. So here's our system. I'm going to define our system as the pulleys, as the two boxes, the pulley, the inclined plane, and the earth. So our system includes everything. And when we do that, it means we don't have any external forces. Nothing is reaching into our system to add energy or remove energy because our system is so big it includes everything. And maybe what I'll do is make a second video where we define the system a little differently so you get an idea of how that changes things. All right, conservation of energy tells us that when I use these capital E's here, I mean mechanical energy. So conservation of energy tells us that the mechanical energy at the beginning is equal to the mechanical energy at the end. And that's only true if we have a closed system. In other words, no external forces, right? Because if something can reach into our system and add energy, then obviously we're going to have more energy at the end than we started with. Or if something can energy can leave our system using some mechanism, then we'll have more energy at the beginning than at the end. So initial mechanical energy equals final mechanical energy only if we have a closed system and if the energy isn't changed into some non-mechanical form like heat. And energy is changed into heat by non-conservative forces like friction and air resistance. Okay, so we want to deal with more real-world problems. So we need to be able to account for external forces and heat, friction, and air resistance, non-conservative forces. So let's start with external forces. If external forces exist, then we modify this equation just slightly. We say our initial energy plus the work done by external forces is equal to the final mechanical energy in our system. So let's think about this. Make sure we put it on the right side of the equation, on the correct side of the equation. If we have positive external force work done by external forces, then those external forces are adding energy to our system. So our final energy is going to be greater than what we started with. So we need to add the work done by external forces to the left side of the equation. So this makes sense to me. If external forces are doing positive work on our system, we end up with more energy at the end. So we have to add that to what we started with at the beginning. Now, let's take a look at the work done by non-conservative forces, friction, air resistance. And we can modify this equation one more time. We have initial energy plus work done by external forces plus work done by non-conservative forces equals our final mechanical energy. And what I want to do is think about this for a second. Does it make sense? Work done by non-conservative forces. How does that change things? It always makes the final energy less than the initial mechanical energy. Because some of our energy of motion or some of our potential energy is going to be lost to heat, right? I use the term lost kind of loosely. It's not lost, it's still there, it's in the form of heat. It's converted, it's changed into the form of heat. But we can't use that for our mechanical energy. We can't account for it in our mechanical energy. So, is it on the correct side of the equation? Well, only if it's negative, and it is negative. And I usually write it right there. Let me highlight it for you. I write it right there. Every single time I write this equation out, I write negative under the work done by non-conservative forces, because otherwise I forget. And if I forget, you'll probably forget also. The other way you could write this, which sometimes is easier so you don't make that mistake and forget a negative sign, is you can write it like this. See, the external forces, the work done by external forces, sometimes that's positive, sometimes that's negative, we don't know. So we can just put it here and hopefully we'll remember when the time comes to keep a negative sign there if it's negative. But the work done by non-conservative forces is always negative. So maybe this is a more intuitive way to write it. We have to add something back at the end. If we have non-conservative forces in our system, we're going to end up with less mechanical energy. So we have to add something to the right side of our equation to keep the equality. But we have to add a positive quantity. So don't forget to put the absolute value bars around the work done by non-conservative forces there. Okay, so what I'm going to do, I'm going to start out with the first equation and start writing some things down here. E initial plus work done by external plus work done by non-conservative forces, and that's a negative number, is equal to E final. Now I like to let's just keep it simple, not think about things yet, write out a full equation and then think about what's not in our system. Maybe we can get rid of some of our types of energy because we don't have that in our system. So we only know of 3 types of mechanical energy right now. We've got kinetic energy, energy of motion. We've got elastic or spring potential energy, energy stored in a spring. And we've got gravitational potential energy. So I'm just going to write them all out here. I've got 2 masses in my system. So mass number 1, there could be some elastic potential energy associated with it in the initial state. There could be some gravitational potential energy associated with it in its initial state. And it could have some kinetic potential energy initially. Mass number 2 could have spring or elastic potential energy initially, could have gravitational potential energy in the initial state, and it could be moving. It could have energy of motion. And then we have work external. We have work done by non-conservative forces, which is a negative number. I told you I always write negative under it. And then at the end, We could have some spring energy for object 1 in its final state, some gravitational potential energy from object 1 in its final state, some energy of motion, object 1 in its final state, and the same for mass 2. So that's everything. We have 2 masses, and we have 3 types of energy that we can have. So now what we want to do is go through and just start thinking about what we can get rid of. Are there any springs in the system? No. So we're not going to have any elastic or potential energy. We're not going to have any spring potential energy in the beginning, and we're not going to have any at the end. Obviously, I could have left those terms out to begin with, but I'm trying to be very general here so you can see the process and apply it to other types of problems that might have springs in them. Is it moving initially? So if it's not, we can get rid of our kinetic energy, right? There's no kinetic energy there if it's not moving. Do we have any external forces? In this case, the answer is no, because we defined our system to include the Earth. We've got no external forces, so that term goes to 0. The work done by external forces is 0. Do we have friction or air resistance? Yes, friction. So we need that work done by non-conservative forces term. Can't set it to 0. Are they moving at the end? Yes. Both boxes will have kinetic energy at the end. So let me rewrite this, see what I have now. I've got a gravitational of box 1 in the initial state, and a gravitational potential energy of box 2 in the initial state. We've got a work done by non-conservative forces, which is going to be a negative number. We've got a gravitational energy of box 1 in the final state, gravitational energy of box 2 in the final state, and they both have kinetic energy. Kinetic energy of 1 final and a kinetic energy of 2 final.